In this video, we're going to talk about sets. Now let's start with the definition of a set. A set is an unordered collection of objects. Now, I took this definition right from the textbook, and I wanted to make a note that most definitions I've seen of the word set have not used the word unordered. They've primarily used the word well-defined, or phrase, I should say, well-defined. I believe the reason the author chose to put unordered has to do a lot with some of the examples that we see. But I wanted to make a note of that because well-defined is typically more used since the definition of set is very open-ended. To say that it's well-defined means that when you define a set, when you state what it is, you know exactly what belongs in the set and what doesn't. But to talk about unordered is such an interesting choice. So we'll kind of see how that unfolds as we go through the class. So here's some examples. The students enrolled in math this term, the number of chairs in a classroom, or multiples of 5. All of those are examples of sets. You know right away what belongs in the set and what does not. Okay, so we're going to go through a few definitions here, and I apologize that we're just going to step through them and get some examples and notation. And then we'll kind of move on from there. So objects in a set are called elements. Members is also a common name to use. So elements are members. And a set is said to contain its elements. So we use this symbol to represent element. It's the Greek letter, lowercase letter epsilon. And when you say little a, epsilon, capital A, that's saying that little a is an element of the set A. All right. If it's not an element, we put the little slash through there. Okay, so let's talk about different notations we use for set. Again, the book denotes roster notation differently. The book calls it roster method. Most time it's referred to as roster notation. So roster notation is when the sets are listed, if it's possible. If that's not possible, then they're listed until we have a pattern implied. Okay, so let's see. For example, the set of all vowels, and we're calling it V. Here's how we would list the vowels. So A, E, I, O, and U. And we're referring to vowels in the American alphabet. Okay, so that's how we would list that, all the elements of that set. And just so we're clear, in this particular example, U would be an element of V. That's how we'd state that. The set of positive integers less than 100. Okay, so I'm going to start listing those out. 1, 2, 3, but I don't really want to list out all of the numbers until I hit 99, right? 99 would be the last one that's less than 100. So I'm going to go ahead and use the ... to imply that the pattern is going to continue until we hit the number 99 and then we end. And they do call the ... that has a special name. I believe it's called ellipsoid. I don't think I made a note of that. That's all right. Okay, so order is not important, just so that we're clear. We can say that, let's say if S equals the set A, B, C, D, then we can reorder that anytime we want. I could have called that B, C, A, D, and that's the same thing. That's still the set S. So the order does not matter. The author wants to make a very distinct point of that. Also, listing more than one doesn't change the set. So if you happen to list an element twice, so A, B, C, D, like let's say you say A 2 times, and then B, and then C like 3 times. I don't know. However many times you want to list it out. It doesn't really matter. It doesn't change the set. That's still the set S because it is still containing the same 4 elements in there. All right. Important sets that you should know, the natural numbers. Now, this is very unique. Most books do not, or most, yeah, I honestly have never seen a single book include 0 in the natural numbers. That I have never seen before. So the author, in my opinion, is taking a bit of privilege with that to add the 0 there. I don't find that to be typical. And makes a note. They do actually, the author does call out specifically that most people do not include 0 in the natural numbers. That is unique to this book. Now, as you can see, they are denoting these special sets with bold letters. And when you're writing, you can't write a bold letter. So often when we write these, we use this like double bar to indicate the special set. So the natural numbers, you usually start with a little double bar on the first line. For the integers, we use a double bar for the Z plus, double bar for the R plus. So the pluses are indicating positives. Complex numbers puts the double bar there. And then the rational numbers Q uses the double bar there. So that's kind of how we write it. And that's how we'll write it in this class, just to indicate these special sets. All right, so let's look at set builder notation. So this actually kind of calls out a specific property in a set. So like right here, the set S such that it equals X, and then the bar here is telling us the condition. So this tells us what the condition is, and the condition is X is a positive integer less than 100. Okay, so if I were to list this set, we actually already saw this earlier. I would call this 1, 2, 3, ... 99 ending. That's the roster notation. But that's how we write it in set builder notation. This set O is actually listed in 2 different ways. We could say X such that X is an odd positive integer less than 10, or we could indicate what set X belongs to. So off the bat, they're telling us X is a positive integer and it's odd and happens to be less than 10. So if we're talking about these numbers, so positive integers, odd, less than 10. So 1, 3, 5, 7, 9. Those would be the integers in roster notation. Okay, so let's write the rational numbers in set builder notation. So here's what makes the rational numbers rational. They are numbers that can be written as a fraction. So if I wanted to write that out in set notation, here's how that would look. So Q equals X such that X equals P over Q. And here's where I'm going to indicate where P and Q are coming from, where P and Q are integers. So we don't want them to be fractions themselves or decimals. So we need to indicate that they are, in fact, integers. They can be negative. We can have negative fractions. We don't want them written as decimals or fractions themselves. And there you go. That's how we could write the rational numbers in set builder notation. Interval notation. So interval notation is kind of a throwback to notations you probably saw in algebra. Best way to describe sets, in fact, you maybe even saw it in trig. If you've taken trig, it's got quite a few applications. It's used to describe a set of real numbers. We'll look at intervals from values from A to B. If A happens to be less than or equal to B, then we can denote these intervals by these indicators. And I'm going to write these in set builder notation so we understand what that means. So when we're saying close bracket A, close bracket B, what we're saying is all values, all numbers, where the number is between A and B. And because it's bracket, oops, that's such a sad looking little inequality. Because it's bracket, we're using the equal to, right? Bracket means equal to. Okay, so in this one, we're saying that X is between A and B again, but this time it's only equal to A and strictly less than B. So that's how we write it using the set builder. So this one would be strictly bigger than A, less than or equal to B. And this one would include no equal to brackets at all, saying it's strictly between A and B. We call, by the way, this first set, when it's equal to on both ends, a closed interval. And when it's open, parentheses, it's an open interval, meaning it has no equal to. So that's some indicators that we'll use, closed versus open. All right. Some things to remember: the empty set is a set with no elements, and we denote it with the circle with the line through it, or we could write like the roster notation as empty, like it has nothing in it. Most books favor using the circle with the line through it, but I mean, sometimes they switch back and forth. Sets can have elements that are themselves sets. So for example, this is the set that contains the natural numbers, the integers, the rational numbers, and the real numbers. And you can even have the set of the empty set. So there is a set that contains the empty set. This is the set that contains the empty set. This is just the empty set. So there's a distinction between these two. Okay, they are not the same. We can have a set that contains the empty set, and we can have what's called an empty set, has no elements inside of it. It's a obnoxious distinction, but they will kind of hammer it into your head as we go. Two sets are equal if and only if they have the same elements. So if A and B are the same, then A equals B if and only if for all X, if X is an element of A, then it is also an element of B, and vice versa. If X is an element of B, it is also an element of A. So it goes both ways. All right, so they show some examples. We saw this earlier where they have it in unordered or in mixed up order as well. Okay, let's talk about subsets. So a subset A, of B, if and only if every element of A is also an element of B. So we use this notation. It's similar to the inequality notation, but it has the curve to it. And that's set notation. So we're saying that A is a subset of B. So everything in A is also in B. And that's indicated where we use the strictly one-way arrow. Everything in A is also in B. Okay. And making a note that the empty set is always a subset of every set. And in this definition, a subset can be itself. All right. And it has to do with the fact that it's almost behaving like an inequality where it's got the equal to bar. Okay. Because this is going to hold true. If you say X is an element of B, then X is an element of B, right? Like it's a strictly one way thing to go. Okay, so there is another way to look at the definition for equality of sets. And that's using logical equivalences. So another way of looking at it is to say that for all X, X is an element of A implies that X is an element of B, and X is an element of B implies X is an element of A. Sorry, that should have a square bracket. Or it's equivalent to saying that A is a subset of B. Oops, sorry, it looks like a C. A is a subset of B, and B is a subset of A. So now that we have this understanding of subsets, we could say that they're subsets of each other. And indicating that they're subsets of each other does indicate equality as well. Okay, now we do have an idea of a proper subset. And a proper subset doesn't have the little equal to bar. Okay, so they start off with the statement, if A happens to be a subset of B, but A doesn't equal B, then we say A is a proper subset of B. Okay, and we have a way of writing this out with the logical equivalence. For all X, for all X, if X is an element of A, then X is an element of B. and there exists an X that's in B, but not in A. Oops. So it's also not in A. So we're saying that B has something extra. It has some other element that it contains that A does not. And I'm going to use a Venn diagram to demonstrate this. So Venn diagram starts off with the idea that we have a universe, okay? And the universe is represented with a box. So there's the universe, which we'll call U. Excuse me. And then inside the universe, we have two sets that we're interested in, the set B and the set A. So B is somewhere in the universe, and A happens to be inside of B, smaller and completely contained within B. That way, anything that's in A is automatically also in B. But it's possible to have things in B that aren't in A, and that's what that extra space is representing. All right. So that's how we would draw this as a Venn diagram. So this is called a Venn diagram. And hopefully you've seen this at some point. They're pretty common. So we'll use them to kind of represent some of these definitions. So Venn diagrams offer a visual way of looking at the sets. Let me kind of get into this a little bit more. Let's draw a Venn diagram that represents the set V, which are vowels in the English alphabet. Okay, so in this case, our universe is going to be the English alphabet. Which is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, X, T, U, V, W, X, Y, and Z. All right, wow, I had a moment there where I started to blink. Okay, so if I wanted to draw this out then, here's my universe. And here is V inside the universe. Now, often, sorry, it's kind of sloppy. Often when we have information about the elements, we can actually list the elements. So since these are vowels and we know what they are, there's A, E, I, O, and U. And then out here in the universe, we have all the rest. So B, C, D, no, E, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Y, Z. And there you go. That's how I could indicate all of the elements now. Because there's so much out in the universe, often they won't include this bogged down version. They'll often just do it with what's only in V, since it's so much smaller, because it's so bogged down to see all of those elements, and be like, okay, just those elements are inside of V, and therefore this is how it kind of looks, and we'll know what's left over outside of V itself. Okay, so let's draw a diagram of A inside of B. Oh, actually here, I did that up here. I did that right up here. I kind of jumped the gun. So I'm going to redraw this down there because this is saying it's a proper subset. And a proper subset then would have A smaller inside of B. Oops. And here's B, my slightly sloppy circle, and here's A. So that would be how this could be drawn. All right, the size of sets. So it's possible to talk about the size of sets. If there are exactly n distinct elements in S, where n is a non-negative integer, we can say that S is finite, meaning we're able to list all of the elements in a set. There's n of them. Otherwise, it's infinite. Okay, so it's obviously possible to have infinite sets. And we use the word cardinality of a finite set. And we use the notation with the little straight bars, the absolute value symbol, like we use that when we are indicating the cardinality of a set A. All right. So let's look at the cardinality of some specific examples here. So in this one, let's look at the cardinality of the empty set. How many elements are in the empty set? 0. It's the empty set. If S is the letters of the English alphabet, how many elements are in there? Well, that would be 26. There are 26 letters in the English alphabet. Okay, so this one actually gave us the elements, and in this we can see that there's 3 of them. Okay, now number 4 is different than number 1 because you see how it has little squiggly brackets? That means this is the set that contains the empty set. So there is 1 element here. Okay, integers, however, I can't list it, so we just say they're infinite. Now, you could actually like abuse notation a little bit and say that it equals infinity. That's a really bad thing to say because infinity is not really something we can equal, but it is an abuse of notation to kind of write it that way. Okay, power sets. So the set of all subsets of a set A is denoted P of A, and it's called the power set of A. So let's look at some examples of this. If A happens to be 2 elements, it contains little a and lowercase b, then all of the subsets are, well, one's possible subset is nothing, the empty set, and that works for everyone. Everyone has the empty set as a possible subset. Another possible subset would be just A or just B. And since we're not talking about a proper subset, itself can be a subset. So AB can also be a subset. And there you go. There is the power set of A. And they mention if the set A has n elements, then the cardinality of the power set is 2 to the n. So in this case, A happens to have 2 elements. So the power set has 2 to the 2 or 4 elements. Which 1, 2, 3, 4. There we go. Okay, what is the power set of the empty set? Well, as I said a moment ago, every set contains the empty set. So the power set of the empty set is the set of the empty set. I know. I told you the author really liked this example, so I was going to keep hammering it. All right, let's look at Cartesian products. So Cartesian products of 2 sets A and B, which is denoted A cross B, is the set of ordered pairs A and B, where A is taken from the first set and B is taken from the second set. We can also list it like this: A cross B, sorry, wow, it's such a weird looking A. A cross B equals all ordered pairs where A comes from the first set and B comes from the second set. All right, so let's look at an example. Let's say A is little a, little b, and B is 1, 2, 3. Okay, let's find A cross B. So we're going to take A or every element from A and pair it up with every element from B. So let's start with lowercase a, this one right here. And I'm going to pair it up with everything in B. So that would be 1, 2, and 3. And then I'm going to do that again, but this time for B. So that's going to be 1, 2, and 3. And there you go. That would be A cross B. List it out. Okay, so it's possible to do it with more than one set. So let's say A is 0, 1, B is 1, 2, and C is 0, 1, 2. Okay. All right, let's list them out. Here we go. Starting with A. And I'm not going to put A. Yeah, that's fine. I'll do it. A cross B cross C. That's fine. And I'll list them all. Okay, here we go. So we're going to start with 0 from A. All right. And then I'm going to do 1 from B. That's how I'm going to start myself off. So 0 from A, 1 from B. And the thing I'm going to change is C. So first element is 0. And then I'll do 0, 1 again, but this time with 1. And then I'll do 0, 1 again, and this time with 2. Okay, there we go. All right. Now I'm going to still work with 0 on A, but now I'm going to switch to 2 on B. So 0, 2, 0 from C, 0, 2, 1 from C, and 0, 2, 2 from C. Okay, cool. So now I'm ready to switch to the other element of A. I'm going to look at 1. I'm going to first pair it with the first element of B. So it's going to be 1, 1. 1, 1, 0 from C, 1, 1, 1 from C, and 1, 1, 2 from C. All right. Now I'm going to pair the 1 with the 2 from B and go through all of C. 1, 2, 0, 1, 2, 1, and 1, 2, 2. And there we go. We got them all listed. 12, 1. Yep, I got 12. Okay, cool. Just making sure I got them all listed. We happen to have a name for these. They call them n tuples. Okay, n tuples. That's like the way of denoting the fact that we have more than an ordered pair. These are called ordered triples, by the way, what I was just working with. But anything bigger than triple, they say 4 tuple, 5 tuple, 6 tuple, meaning if we're listing more than that. They do kind of list out how that looks, or start to list out how that looks if you're doing more than just 3. All right, so let's say we have n sets that we're finding this Cartesian product from. All right, and each one has these elements. All right, then our our Cartesian product is going to look like this if I were to list them out. So a sub 1 times a sub 2. I'm sorry, yeah, not times. Well, it is kind of times. It's a product. And then I keep going till I get to a sub n. All right, so I'm going to end up listing little sequences of a sub 1, 2, ... all the way till a sub n, where each of these are corresponding to each set. So a sub 1 is going with a sub capital A sub 1, right? And I'm referring to this a sub 1. This a sub 1 is getting paired with this one. And this a sub 2 is getting paired with this one, and so forth. So the way we say that generalized is we use the I. So a sub I is paired up with capital A sub I, where I is starting with 1, 2, and it's going all the way to n. Yikes. That's how we list the Cartesian product in general notation. Very big mouthful.